Hello and welcome back to DCD Talks. My name is Zoe Turner and I am a digital portfolio lead for DCD. Now today we're going to be talking about leveraging data centers to keep the grid in balance. This is an incredibly important topic for the current market as well. So thank you so much to Schneider Electric for partnering with us on this episode. I'm so very pleased that we're going to be speaking to Flemming Johansen from Schneider. Flemming, thank you so much for joining us today.
Thank you for being here.
Now, before we begin, I would love to know more about you, more about your career journey so far, and your current role with Schneider Electric.
Yes, sure. So I have been at Schneider for almost 30 years now, and I have been working on or with large UPS systems in that period. I've been working in R&D the whole time, but had various roles during these years. I've started out as a designer for hardware and firmware. Then I have been engineering team lead and system architect. And today I have a position as Senior Principal Architect in our innovation group at DCS, which is the data center systems. And my primary focus area is what has basically always been the control of our UPS system and our power converters. So I lead the digital stream of that part.
Fantastic. Well, let's get into this conversation a little bit. In that relationship between data centers and the power grid, there's a lot to talk about there. But starting off, data centers obviously are growing so quickly. What challenges is this growth creating for people running our power grids?
Yeah, so it is correct. Data centers are growing, not just in numbers, but also in size. A data center of 50 megawatt, as an example, was a huge or large data center if you go 15, 20 years back. Today, we see data centers in gigawatt sizes, and the world is becoming more and more digital. And of course, the increased need for AI is the key drivers for this trend, for these huge data centers. And and this growth represents a huge problem for the grid owners, the TSOs, as the infrastructure is really not sized for this demand. And besides the data centers, other sustainability topics like increased penetration of renewables, the movement, especially in Europe, to EV cars, also pushing TSOs. And all this is resulting in a huge queue if you want to get connection to the grid in many regions because there's simply not power enough. Data centers also has the tendency to cluster in the same areas. So with this growth we are talking about, they become a significant part of the load for an area, and this can cause destabilization if they all disconnect at the same time due to a small glitch on the grid. And this disconnection, this will create an imbalance between the production and the demand side. And this will give frequency problems and destabilization. So in order to cope with that, we see regulatory for large electrical loads. They are emerging from different TSOs now all over the world, basically, stating that these large loads has to ride through smaller disturbances without disconnecting. So these are the so-called FRT requirement or fault ride-through requirements.
Well, you bring up that phrase of fault ride through. Can you explain what this means for someone who's not an engineer?
Yeah, I can try. So the main load of a data centers are actually servers that are sitting behind a UPS systems or backup systems. These UPS systems have historically been designed to protect the load whenever the grid has a disturbance. Even though it's a small disturbance, they are protecting the load by disconnecting from the grid and then use power from internal batteries to power the critical load. And it doesn't matter the size of the disturbance, as it's just a small glitch, they will disconnect. So based on this new situation and what the regulatory is saying is that this approach is actually no longer appropriate. If I should try to use a picture, if you could imagine two persons standing holding a rope, each end of a rope, having one representing the data center and the other one representing the grid, then if you could imagine that when the data center needs some power, he starts pulling on the rope, and the person representing the grid, he is trying to keep balance, so he's pulling in the other direction. So they reach a balancing point where their pulling force is the same, and this is their main mission. You could say they need to keep balance both on the load side and on the demand side. So these two persons has the same pulling force. Now imagine that the grid person, he's standing there with the rope, everything is okay, and then suddenly his foot slips just for a split second. What will happen? Well, he would be losing his grip just for a short moment, just to regain balance. The data center person that is standing on the other end of the rope, he feels that the change in the pulling force, and if he was using the old approach or that we traditionally had of UPSs, he would simply let go of the rope, and then the grid person, he would fall over because now he's totally out of balance, and he would have to raise himself again and start all over again. But with fault right through, this approach is more like when the grid person, when he feels that uh, the grid person is actually losing or decreasing his pulling force, he should not let go. He should instead decrease his pulling force on the rope and then help the grid person regain his balance. And when he regains the balance, they can then again pull with full force again in both ends. Now the balance is now kept, even though there was a small glitch on the grid.
That is fantastic. Thank you so much for illustrating it for us as well. I think that really makes sense. In the case then of that approach of fault right through, what does staying connected actually look like for this relationship between data centers and the grid?
Well, so as mentioned from before, right, the load of data centers are protected by UPS, and the majority of a data center load is actually a UPS. Now, a UPS can operate in double conversion mode, which means that the AC power from grid is converted to DC power, and the DC power is then again converted back to AC power that feeds the servers. This is effectively isolating all the input performance from its output performance. So it really separates these two things. So everything that happens on the grid side is not seen on the server side. Now, when a voltage dips now occurs, the UPS will react depending on what is the depth of this voltage dip. As an example, if it is less than 50%, the UPS will be acting in what we call a mixed mode, where a portion of the power to the load is taken from grid. Basically, we are taking all the power that we can from grid, even though that the voltage is lower. But the rest is then supplemented from the stored energy that we have on the battery. So this is one scenario for a load dip. But it could also be that the voltage drops even further down, so below 50%. What will happen there is that the UPS will start drawing any power from grid and take basically all the energy from battery. And the reason why it's a different behavior is that we don't want to load the grid while it is almost in its knees in voltage, right? So we want to help it recover. If the grid then recovers very fast, then the UPS will then do what we call a fast transition back to grid operation. So if I go back to my picture, as soon as the grid guy is on his feet again and ready to pull, we will of course pull from the data center side, so the balance is kept. The fast transition back to grid operation. This is what in regulatory is stated as PFAPR, or post-fault active power recovery. And this is a number they would say this is the time, the maximum time you have from when the grid returns till you go back to full to draw full power from grid again. In a UPS that we have designed, right, we can do that within 0.3 seconds, and this is basically within all the requirements that I know of at this point from different TSOs.
0.3 seconds. That's impressive. I mean, you've mentioned as well, this is kind of the case when you see dips in the grid. Is that also the case, or does this kind of apply as well when you see spikes in the grid? Let's say your grid guy holding the ropes is jumping. Do you see the same kind of take the same kind of approach?
Well, if you see spikes or voltage swells, well, typically they would come after a dip, right? Because the grid has to settle again. If I go back to my picture of the two persons that are pulling in the rope, think of it as at the point where the grid person is regaining balance and he starts to increase his pulling force. He's pulling a bit too much, like a reaction to he had lost some pulling force. Now he's pulling a bit too hard. The data center guy should not let go of the rope. In this case, he should still just let him pull, and then so they can regain balance again. There's no post-fault active power recovery in the situation where you have a voltage swell, but this is because you have basically voltage all the time, versus if it was a dip, the voltage now can almost disappear. So that's the difference why there's no post-fault active power recovery in voltage swell situations.
That is fantastic. Thank you for clarifying that for us. Now, unfortunately, we are quickly running out of time, Flemming, but I would love to know as well, if I am building or running a data center, what is the first thing I need to check to ensure that I am being we'll call it a good neighbor to the grid? How do these two, gentlemen pulling a rope ensure that they are good neighbors to each other?
Yeah, so first of all, if you're building a data center, you need to understand which FRT requirements apply to your area, because unfortunately there's no harmonized standard at this point. So each TSO has developed their own set of standards. So you need to understand what applies. Second thing to notice is that these requirements are valid for the data center, not the UPS. Typically, requirement states that the load of the data center must resume at least 90% of the power that was there before the incident. It means the UPS will recover to 100%, but you also have mechanical loads. So you must consider your mechanical loads as well, because maybe they will not recover for a voltage dip. Or maybe you need to put some of this behind a UPS as an example, in order to reach the requirements. And the third thing you need to be aware of is simulation models. So grid owners, they are starting to require that you, as if you build a data center, that you deliver a simulation model of your data center so that you can demonstrate by modeling what is the behavior of the data center during an outage. And you can demonstrate the fault right-through behavior, because they want to simulate different fault scenarios on the grid, and they want to have a model on how the data center behaves. a small remark on the regulatory. So many of these local requirements that you find today, they are still in draft and not mandatory at this point. But we still see that TSO are requiring compliance, even though they are not put into force yet. So it can be a little tricky as the requirements can change basically before they are put into a mandatory state. So keeping a close conversation with the TSO is really a good advice here.
Well, Flemming, thank you so much for taking the time to speak with us today. Now, we are running out of time, but I would love to know, what are your final thoughts? What should our audience take away? And what should they really take away from this discussion?
Well, I think the takeaway is that they should think about, if they build a data center, that they need to be a good neighbor, right? So when the grid stumbles, the data center should be there helping to regain balance. That's one of the takeaways I would like the audience to have. And also, if you're building data centers, you need to understand what are the actual requirements in your region. You need to consider your mechanical loads in the data center. And you must expect that the TSO will request simulation models, as an example. And as I mentioned, the tricky part, regulatory is still evolving. And of course, we are following this closely, and we will, of course, adapt products in the future if needed. But you can follow that on the website or on social media for Schneider Electric. Yeah, thanks.
Excellent. Well, Flemming, thank you so much for taking the time to speak with us. It's been an absolute pleasure, and thank you so much for your insights. Thank you as well to our audience who are watching at home, at work, or on your commute for joining us on DCD Talks today. Don't go anywhere, as this episode will be on demand shortly, so you can go back and watch it again. Thank you as well to Schneider Electric for partnering with us. Don't hesitate to reach out to them. As Flemming says, if you have any questions, I'm sure they would be happy to discuss this further. Until the next time, on the DCD Talks channel, thank you so much for joining us, and see you soon.